start this recording. Let's go ahead and share my screen. Okay, we're back. Okay, so this const. Yeah, so this at the beginning, right here, this const is basically referring to the return type being const, right? So once again, just undefined. Oh, because I made it a part of my class. Okay, that's why. So I'd have to make a new class here. And what did I call it? My class, like normal. Um,
When you have the return type a constant int, right? But you have as a protected function, like what can you really do? Can you actually do stuff inside of the
yeah,
function?
you meaning like if the function is like completely like made const, like what can you even do?
Yeah.
Yeah, so you can still like do a bunch of stuff. You just can't manipulate your own values. And then returning it as const, and that's what I'll go over here. Really, only matters is if what you're capturing, like on the left hand side, is also const. So for instance, if we just left this as like int a, even though like this function is returning a constant, I can go ahead and still change the value of a.
Because
Um,
A is a constant.
exactly. So it's still like it still relies on the fact that you need to make sure you're capturing it with a constant value. So in which case, now we can't do that. So um, so the other constants we have, this one is the parameter. So const on the actual parameter. So when that's the case, you can't change like what my int is equal to. Even if it's just a copy, you can't alter that value. Let alone the fact that even if we did alter this, it wouldn't be persistent in memory later on. But this is to protect your parameters to make sure that you as the developer aren't doing anything you shouldn't do. Really, most of the time these consts are really to save ourselves from ourselves, right? So that we can make sure we're not doing anything dumb with our code. The last const, that's all the way on the right hand side, this is the one that protects this value. So we can't edit what my variable is within the class because it's protected with const, which I think I may have said protected, but it's read only is what we define this as. Most of the time you see this with getters because when you call a getter function, its core piece of functionality is just to give you something back. It shouldn't be changing anything. And really, this just guarantees that our functions are doing like only one thing, right? If their job is to give you back some piece of information, they shouldn't be doing anything else. So it's kind of like the single use responsibility or single something like that. It would be protected without the this in front. Yes, you are right. So even if we took the this out, it would still be protected. Good question. I did the this to make it that much more clear, but 100% we can't change this even if we took the this off. Yep. Cool. So that's pretty much everything there is on the consts. What else do I have in here? Okay. Command line arguments. So this is something I didn't go over in my labs specifically, but I saw it on the review sheet, I think. So this right here is the like int main. So by doing these parameters, int main is just a function, so it can take in parameters, right? So to take in command line input, what we want to do is um, have the first parameter be the number of arguments. So that's why you typically see it as argc. That's just the arg count, right? So it's an integer. That's how we know how many arguments are in there. The second thing is a double character pointer. Basically, it can be treated as an array because it is, and it's a character pointer because character pointers are just strings. So basically, it's an array of strings. That is what a double character pointer is. Okay, that's why it needs to be these double stars, and then argv, which I think is just like the argument values, I imagine. So if we go ahead and compile this and then have it crash and then figure out what we messed up. Okay, and then we rerun it. And okay, so we can go ahead and do like pointer example. And then now we can just start passing in arguments, right? What I've done here is just a for loop. So we print out how many arguments there are, and then we go over a for loop of as many arguments and print out all of the arguments I passed in. So it's like these are arguments in my list. And then I go ahead
So
and
why
hit
don't
enter.
you use My bad, my bad.
You're
The
good.
the two asterisks again. I get got confused with that again. The double asterisk.
Yeah.
Is that because
Yeah. So with the char like double pointer, so just a character array itself, that would just be a string, right? A string is just made up of a bunch of
Mhm.
different characters.
Wait, is that not oh, so you're not passing in a string?
We're passing in a array of strings. So
Oh, okay, okay, yeah, yeah, my bad. Okay, yeah, yeah, that makes sense.
cool, cool. Yeah, yeah. So we can just basically iterate over this, and then each individual element in argv is actually going to be its own string, which is pretty helpful because then you can just have your user pass stuff in here, and then just parse through that however you need to be. Usually, this relies on the fact that like your application understands like, oh, the second argument is going to be this value, or the third argument is going to be this value. So you can just index this argv accordingly. Something important to note is it does count the name of the executable as the first argument. So that's also printed out here. Um,
And
one,
real quick,
two.
just to understand, in theory, when you have a constant character, it will be the length plus one, right? Because it has the null, one null to end the string or whatever, right?
So actually, it'll just be seven. So that's not actually counted in the count. So there's seven arguments here, so it's just seven. So you don't have
Yeah,
to
yeah,
worry
yeah.
about any like plus one
But
or
like
anything.
in theory, like if they ask us a question about like how it's like built, how the strings are like made, like doesn't it have that one extra, technically that one extra like null character to kind of like signify that's the end of the string?
So I think strings have that. I don't think the character array has
Oh,
that, and I don't think they're putting them in there. So like if it's an exam question, like this argc is like literally the exact amount. Like I had the seven
yeah.
printout, and it went ahead and print seven different arguments out.
And
So
does a string class manage its own memory?
it does, although I don't think there's any like well, if you made a new string, you have to handle that, right? Because you called a new
Yeah.
keyword. But if for whatever reason a string class is doing dynamic memory, which I'm not sure if it does, it would handle all of it.
Okay.
Yep.
Thank you.
Yeah, no problem. Okay, so I think that has to do with okay, so command line arguments, good to go. Get const stuff. Okay, so now I think we're on to inheritance. The other stuff is a little bit quicker. So inheritance, especially because we kind of just went over the other stuff here. So let's see here. Did that with a vehicle and vehicle header file. Okay, so um, here I think I used the header file over. Actually, I may have done this one. I used this one. Okay, so looking at this, this is inheritance, and as you guys remember, with inheritance, we get polymorphism, right? So that's kind of a benefit of using inheritance. So with this class vehicle, this is going to be our abstract base class. We know that just because we have some virtual functions here. There wouldn't be a constructor in an abstract base class. I think I threw that in there for some demonstration purposes, but because an abstract base class can't be instantiated, there's no reason for it to have a constructor, right? And actually, I say that the I think the base classes might, or the child classes might be able to use this base constructor. That might be the case, but definitely these are virtual because they're going to be filled out by other classes. So this set cost function that we've set to virtual, that's going to be filled out by these other classes. So the two child classes, car and truck, are going to have their own set cost functions that they're going to basically define what they do specifically for that class. And that's the whole purpose of this inheritance, right? So that you can kind of give a skeleton code of what a lot of classes are going to use and then have those classes fill in the blanks from there. Okay. Um, here we have the car class, which is inheriting publicly from vehicle. So anytime you have public inheritance, that is a relationship. So a car is a vehicle. Anytime you have a private relationship, which I have here, that is a car has a engine, right? That's that relationship. So there's is a and has a. public is and private is has. Most of the time, if the developer's doing a good enough job as they should be, it should read like okay, meaning like a car, is a vehicle. You would never say like a car is a engine, right? If you find yourself making something like that, you probably need to take a look at your design, right? So most of the time, those are relatively obvious, assuming the naming convention and everything is fine. Um, so within the car itself, this is how we're actually going to construct the car and how we're going to construct a private has a relationship of this engine. So this will actually go ahead and call the engine constructor here by doing this line. Where it passes the number of cylinders into the car, and that's just going to forward it to the engine itself. Set cost. So this is just basically setting the cost of the car, which it's different than how the truck does it, and that's the whole point of this whole inheritance business. The truck also has another value associated with it, which is the towing capacity, and the set towing capacity. So a car doesn't have that, and obviously neither does a vehicle. So that is very specific to a truck. That'll come up a little bit later. So anytime we want to deal with the concept of polymorphism, we actually need pointers to be involved. The reason we need pointers to be involved is so that we can have this idea of upcasting, where upcasting is going to basically allow the polymorphism to actually occur. So when we do upcasting, that's on line 94, what you're basically saying is like my truck is going to be converted into a vehicle. And when this happens, vehicle truck, which is like the new variable that my truck was copied into, basically anything that was associated with the truck specifically is going to be kind of dropped off or left out of the mix when we convert it to a vehicle. So like vehicle, for instance, isn't going to have a towing capacity associated with it. That's going to be kind of left off. And that's okay. That's just what's going to happen. And basically, we use this concept of upcasting when we are able to make a vehicle of vector pointers and push both the truck and car back because their parent class is a vehicle. So we can store them kind of in the same data structure. So that's kind of something we haven't seen before, where you can have something that are two different types, but because they share a parent class, they're able to go into the same parent class data structure. This gives us the ability to kind of loop over these objects and call the same exact function on them, even though this function is going to call two different definitions based off of what the object actually is at its core. So for instance, when the car goes through here, it'll call the set cost function for the car. But when the vehicle does it, it'll call when the truck does it, it'll call the truck's set cost. And then the same goes for the display function. So that's kind of the general concept. What are your questions?
Yeah. So you can create like, so basically when you create like, let's say you have a bunch of cars that are vehicles, right? So they have is a relationship with a
Yep.
vehicle, so they inherit vehicles. So then to enable to like kind of access all of them like easily, you would create a vector of vehicle pointers, right? Which you create there,
Hmm.
and then the way you start accessing them is yeah, so how exactly would you like access? Because I know I from what I remember, obviously I haven't gone back and studied yet, so I don't
Hmm.
remember that much of it. But
Yeah.
like for example, if you have a member function in one, if you have like if you have member function in like two different vehicles, it'll kind of like find something like it'll like find it'll know which one belongs to. It'll call the appropriate one, right?
Hmm.
Something like that. I don't remember.
Yeah, that's kind of the idea here. That basically, like, so I'm pushing these back into vehicles, and then when I
Hmm.
loop over the size of the vehicles, it'll just index, and then basically whatever's at this index, whether that's the car or the truck, it will call the set cost function on it accordingly. So I think that's kind of what you were saying, where like if I
Right.
click
Yeah.
on set cost, it'll bring me to the actually just defaulted to bring me to the trucks one, but really it's calling this virtual set cost, and then it will basically figure out if it's a car or if it's a truck, and then call either this set cost or this set cost.
Mm-hmm. Makes sense.
Yep. Cool. Any other questions on this?
when you do vehicle,
Mhm.
me truck is equal to my truck. Is that where you're that's where you're upcasting it, right?
Yeah. So this is just an example. I actually don't do anything with vehicle truck. But
Mhm.
the same concept is happening when we do this push back. It's upcasting.
Yeah. So vehicle truck is a vehicle. Oh, okay, and you're equaling it to a truck, right? A my
Mhm.
truck. Okay.
Yeah. Actually, I say that I'm not sure if the exact vehicle. Let's see here. Yeah, I don't know if the exact like upcasting principle is happening, but it's probably got the same kind of idea where you're making a my truck, kind of become a vehicle in the data structure. Something that I didn't mention is this idea of downcasting, which like doesn't even work based off like the actual
Yeah.
compiler. Where if you try to make this would be a my vehicle here. Here, this doesn't make sense because we can't actually instantiate a concrete version of a vehicle because it's an abstract base class. But if we were, this downcasting still wouldn't work
Hmm.
because my vehicle doesn't have a towing capacity. So when we try to convert that to a truck, it doesn't have the space associated with like a towing capacity to even create one to begin with. So there's
Yeah.
nothing to copy over. And rather than just leaving it blank, it just doesn't work at all. So it's one thing to upcast and kind of leave more detail away than trying to downcast where you're trying to create more detail, where you're trying to convert to something that already has more detail, and you just can't do that. So downcasting is something that's just not going to work.
Hmm. And what's the difference when you see you made it a pointer there? You made v truck a pointer, right?
Yeah.
What would the difference if you would not have made it a pointer? Like, is
Um, well, the reason I made it a pointer is actually because like my truck is also a pointer because it's like
oh,
using some
mhm.
new calls. Otherwise, if like my truck was a pointer, I don't think I need to make this a pointer. I
Yeah,
just made it a pointer to begin with because that's the only way you can get polymorphism behavior.
yeah, yeah.
Yep.
Makes sense.
Yeah. Good questions. Okay, so that was the quick version of inheritance. So we have maps next. Okay, so maps. Um, so the important things to note from the maps is just what the key and value are. So the key is the first thing typed in the map, and then the value is the second. The key is what you're going to have as the unique keys. Maps have unique keys, so you can't have duplicate keys. And then the values, those can be duplicates all you want. I like to think of it just as like a simple function, like on a Cartesian plane, just with some x and y coordinates. Um, in a function you can only have one x value, but you can have multiple y values all you want, so horizontal lines and not vertical. Same concept here, right? You can only have individual unique key values. So keys and values each can be like integers, characters, strings. They can be entire objects. It's not really limited in that case. uh, so when you do try to add a duplicate key, if you try to do it using the in place function, um, that's basically that's the in place function is going to go ahead and not actually make that duplicate. It's going to just ignore this completely. So when we try to run this, let me go ahead and do that. Um, let's see here, map dash, and then we just want to call this. There we go, map, and then let's do. So when we try to this outer range is happening from something I think I'm doing out there. But when we try to emplace this right here, you can see that what it prints out is still just 23, and it never actually used that 15 that we try to emplace with. Um, so um, that's kind of the behavior there. So it just ignores the in place. Now, doing this is a little bit different. This is actually indexing a key that already exists, and this will go ahead and overwrite what we were doing. So this will be a 15 now. So if you need to change what you've already put, that's one thing, and you need to index it using the bracket operator. But if you try to emplace it, it's just going to ignore it because it's like, hey, this already exists. So and then with values that don't exist within a map, you can still go ahead and print those out. They're just going to be blank. So for instance, here, we can go ahead and try to access the E key, which doesn't exist in this context. And it will basically just print out nothing. And that's the case if we made these integers as well. Like if the values were integers, this would actually just print out a 0. So it doesn't give you an outer range or anything like that. It's just going to be blank. What will give you an out of range is if you try to use the .at, which is why I was breaking before, because I was using the .at. And doing this, because E doesn't exist, this will give you an out of range. So you can kind of decide, why you're using a map to begin with, and then like what functionality do you want from your map, and then depend if you want to use like the in place function, or if you want to index it like this based off of if you want it replaced or if you don't. And then down here, like if you want it to actually throw a warning like, hey, like this doesn't exist, or if you just wanted to print out some blank stuff or something like that. So that's kind of up to you guys, but it does have options. So that's kind of how the maps work. Let's see, any questions on those? Okay, so the next one's just the bitwise stuff, which I think we went over like 2 weeks ago, so I won't actually go through and run this. What I will go through, which I didn't really go through in lab per se, was understanding like just either how to do things by hand or like what's really going on. So if we take a look at, we'll just go down the list here. So if we just start at the OR, and we have, let's see, I already don't like that. We have like a 1, 1, 0, and then 1, 0, 1 paired with a 1, 0, 1, 1, 0, 0. Okay, we'll do this. So this is just like 6 bits. If we did the OR, let's actually forget about these. I'm just going to do a 4-bit thing. So if we did an OR here, this is going to be a 1, 0, 1, and 1. So basically anything that has a 1 in it at all is going to be a 1. This is like an if statement with a OR. And if just one of these things is true, they're all going to be true, right? If we do an AND of these things, we're going to get a 0, 0, 1, 0. So anything that has any zeros at all is going to be 0. So if there's at least just one false, it's going to be false. The only time it's true is if there's 2 of them. The XOR, this one's a little bit different, but anytime that they're different, we're going to get a 1. Anytime that they're the same, we're going to get a 0. So this one's going to be 1, 0, 0, 1. Because this will produce a 1, this will produce a 1, these two in the middle will produce zeros. Negation, this one's really easy. This will just like flip the bits. So for this one, for instance, you just get 1, 0, 1, 0. And then for this one, you'd get 0, 0, 1, 1. Bit shifting, so we can kind of do that one here. So if we shift this value to the left by 3, let's say, we're going to go ahead and obviously shift it left this way, which means these 3 are just going to kind of fall off. And then the rest, the right-hand side is going to get padded with zeros. So you're going to have a 1, 0, 1, 0, 0, 0. And then if we go ahead and pad this, or not pad this, but shift this to the right, so this same value, the left is going to get padded with zeros. And then these 3 here are just going to kind of fall off the edge, and we're going to get 1, 1, 0. The left shift and right shift are usually used with like multiplication and division. So if you have just this 4-byte value, that's 0, 0, 0, 1, this in decimal is just a 1, right? If we shift this to the left, that'd be like multiplying it. We'd get 0, 0, 1, 0, where in decimal, this would be a 2. And then if we did it again, we'll do it up here. This would be 0, 0, 1, 0, 0, which that would give us a value of 4. So you're basically multiplying it by 2 when you do this. And then if you shift it to the right, you basically go backwards and you're actually dividing it by 2. So that's kind of where the shift left, shift right thing kind of comes in handy. But yeah, this is pretty much like the kind of stuff you guys need to know for the exam, paired with understanding what each of the, that was a terrible line, understanding like what each of these syntaxes are. So negation, XOR, and or, and then shift left and then shift right, basically depending on where the arrows are pointing to. So
I have a quick question.
yeah.
Like, let's say for variable one, variable two there, like how do you the what's called the binary representation of that, like for 240, wasn't one one, so is that binary, is that an octal?
This or
Yep.
this is a binary.
Okay, this is binary.
Mhm.
Okay, yeah,
Yep.
that's it. Then it, for basically what it does is it kind of implicitly puts it into binary, and then when you kind of use these bitwise operators, that's when it kind of does
Hmm.
that stuff. So if you have variable one, variable two, and you do like for example and, right, all the
Hmm.
ones that have, so if you look at the variable one, variable two, only like the last two digits of the first like row kind of would be ones, right?
Yep. Just these right here. Yep.
Mhm.
Yep.
Okay. And to actually do that, write that in code, how would that work? Would you do variable one and variable two like that?
Yeah.
Or
It's just this right here.
oh, okay, okay, yeah, I didn't
Yep.
see that.
Yep.
Okay.
Um, yeah. Sorry, I don't know. You may not have come to this one, but this one I just made a function that basically formats it and prints it out.
Yeah,
But
yeah, yeah.
all of the operations are happening like at the
Mhm.
end here. So these are where all the actual operations are happening.
Yeah, yeah. No,
Um,
I remember. I
okay.
came. I
Okay.
just
Cool.
hadn't watched the lecture for that week, so just that was like the first
Gotcha.
time.
Gotcha. Gotcha. Yeah. Cool. Cool.
Okay.
Any other questions? Um, Now it's pretty much where I'll just, if you guys want, I can open up the questions to anything you guys might need, because I think that's everything I had planned. So
Can I ask a specific question about the project?
yeah, we can do that once I'm done recording everything. I'd be more than happy to answer that. Yep.
Sounds good. Thank you.
Yep. Okay.